Search in rotated sorted array. Let's raise the stakes. What if the array you're searching in is sorted, but then suddenly rotated at an unknown pivot? Search in rotated sorted array is a Pattern Mastery 100 superstar and a go-to interview question at Google, Facebook, and Apple. So many candidates try to flatten the array or revert to brute force, but with the right approach, you can use binary search to find any target in O log n time. Mastering this pattern proves you're ready for real-world coding challenges. Let's see how it's done. Let's break it down. You're given a sorted array that's been rotated at an unknown point, and a target value. You need to find the index of the target, or return -1 if it's not present. No duplicates, and the array is still mostly sorted, just with one pivot. Now let's assess. Scanning every value is not good enough for large arrays. Because the array is made of two sorted halves, we can adapt binary search. At each step, we determine which half is sorted, then see if the target lies within that half. This halves the search space each time. Classic O log n efficiency. Here's the structure. First, set left and right pointers at the array's ends. Then, while left is less than or equal to right, find mid. If nums at mid equals the target, return mid. If nums from left to mid is sorted. If the target is in this half, move right to mid -1. Else, move left to mid +1. Otherwise, meaning the right half is sorted. If the target is in this half, move left to mid +1. Else, move right to mid -1. Finally, if not found, return -1. Let's try to implement it using solution 1. We're defining a function called search that takes an array nums and a value target. We loop through the array from left to right. At each index I, we check if nums I is equal to target. If it matches, we immediately return I, because we found the target's index. If we finish the loop without finding a match, we return -1 to indicate the target is not in the array. Time complexity is O(n) because we may scan the whole array. Space complexity is O(1) because we only use one loop variable. Let's verify solution 1 for search in rotated sorted array. Input is nums equals 4, 5, 6, 7, 0, 1, 2, and target equals 0. We start checking each index. At I equals 0, value is 4, not 0. At I equals 1, value is 5, not 0. At I equals 2, value is 6, not 0. At I equals 3, value is 7, not 0. At I equals 4, value is 0, which matches the target. So we return 4. The output is 4, and the expected is 4. They match, so solution 1 is correct for this test case. Now let's try to implement it using solution 2. We're defining a function called search that takes an array nums and a value target. We set two pointers, L at the start of the array, and R at the end. Now we run a loop while L is less than or equal to R. Because we're doing binary search, inside the loop, we compute mid as the floor of L plus R over 2. If nums mid equals target, we return mid immediately. If it's not equal, we need to figure out which half is properly sorted. We check if the left half is sorted by testing nums L is less than or equal to nums mid. If that's true, then the left side from L to mid is sorted. Now we check if the target is inside that sorted left range. Nums L is less than or equal to target, and target is less than nums mid. If the target is in that range, we move R to mid -1 to search left. Otherwise, we move L to mid +1 to search right. If the left half is not sorted, then the right half must be sorted. So we check if the target is inside the sorted right range. Nums mid is less than target, and target is less than or equal to nums R. If it is, we move L to mid +1 to search right. Otherwise, we move R to mid -1 to search left. If the loop ends, it means we never found the target, so we return -1. Time complexity is O of log n, because we cut the search range in half each step. Space complexity is O of 1, because we only use pointers and variables. Let's verify solution 2 for search in rotated sorted array. Input is nums equals 4, 5, 6, 7, 0, 1, 2, and target equals 3. We start with L equals 0, and R equals 6. Mid is floor of 0 plus 6 over 2, which is 3. Nums mid is 7, not 3. We check if the left half is sorted. Nums L is 4. Nums mid is 7. So 4 is less than or equal to 7, meaning the left side is sorted. Now we check if 3 is in the left sorted range from 4 to 7. But 3 is less than 4, so it's not in that range. So we move L to mid +1, making L equal to 4. Now L is 4, and R is 6. Mid is floor of 4 plus 6 over 2, which is 5. nums mid is 1, not 3. We check if the left half is sorted. Nums L is 0. Nums mid is 1. So yes, the left side is sorted. Now we check if 3 is in the left sorted range from 0 to 1. It's not, because 3 is greater than 1. So we move L to mid plus 1, making L equal to 6. Now L is 6, and R is 6. Mid is floor of 6 plus 6 over 2, which is 6. Nums mid is 2, not 3. We check if the left half is sorted. Nums L is 2. Nums mid is 2. So yes. Now we check if 3 is in the left sorted range from 2 to 2. It's not. So we move L to mid plus 1, making L equal to 7. Now L is 7, and R is 6. So the loop ends. We return -1. The output is -1, and the expected is -1. They match, so solution 2 is correct for this test case. Let's recap search in rotated sorted array. The big idea is learning how to search efficiently even when the array looks disrupted by rotation. We're given a sorted array that's been rotated at an unknown pivot, and we need to find the index of a target value. Even though the array looks broken, it still contains sorted structure. Each side of the pivot remains ordered, so the goal is to use that structure instead of scanning everything. A linear scan works, but it's ON, which doesn't scale well. The key insight is that rotation doesn't remove sorting, it just shifts it, so we can adapt binary search. The critical skill is identifying which half is sorted at each step, then using that information to decide where the target could still be. We keep 2 pointers, left and right, and repeatedly compute a midpoint. At each step, we check whether the left half is sorted or the right half is sorted. If the target falls inside the sorted halves range, we search that side. Otherwise, we move to the other half. Each decision cuts the search space in half, just like classic binary search. We implemented this successfully on LeetCode without errors by looping through the narrowed range, checking the midpoint, determining the sorted half, and adjusting boundaries until we either found the target index or concluded it wasn't present. LeetCode test cases confirmed correctness. For 4, 5, 6, 7, 0, 1, 2, with target 0, the algorithm returned index 4 as expected. And for the same array with target 3, it correctly returned -1, showing the search logic works both when the target exists and when it does not. The takeaway is that patterns matter more than appearances. A rotated array may look scrambled, but its partial ordering is exactly what makes an O log n search possible. Once you learn to spot the sorted half each time, you can turn a broken array into a predictable binary search problem.